In this video, I'd like to talk about the math question of the day for Sunday, June 4th, 2023. And with this example problem, we need to show that this series here, this infinite sum, is divergent. We need to show that it does not approach any real number as we add more and more terms. And questions like these tend to be taught in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through it. And with series and showing that they are divergent, there are two main approaches that we can use. The first approach is fairly complicated. If we know a formula for, let's say, the ith partial sum, then we can take a limit as I goes to infinity and show that that partial sum formula approaches infinity, that it is divergent. For instance, let's say, for example, that we have the sum of the first n terms, and we will say n starts at 1 and goes to I. We can come up with a formula for this. Let's call this equal to s sub I. The partial sum formula for this would just be I multiplied by I plus 1 and divided by 2. And we can show that in the limit as I goes towards infinity of this formula for the ith partial sum of this, that this is equal to infinity. This would be divergent. But the issue with this approach is that most series have either very complicated partial sum formulas or they are incredibly difficult to find. As you can imagine, this is one of the simpler series that we can define, and it is difficult to find this formula. So unless we can find this formula for the partial sums, we can't take this approach. But luckily, there is another much simpler approach to show that a series is divergent. And let me paste in the theorem that we're going to use. It's called the divergence test. And with the divergence test, basically, if we have some series where we're adding up the a sub n terms, and we know this converges, then the limit as n goes to infinity of these terms here in the sequence, this has to approach 0. Or in other words, as n goes towards infinity, this term here, the terms that we're adding up, have to get smaller and smaller. They have to approach 0. And if we can show that in this limit, in this case, this right here is our a sub n, in this limit, if we can show that as n goes towards infinity, that this does not approach 0, then we can conclude that it does not converge. So convergence guarantees that the terms get smaller and smaller and approach 0 as n goes towards infinity. However, you need to be careful with this divergence test because the converse is not true. It is not true that if we know that the limit as n goes to infinity of these terms here, if this limit is equal to 0, it does not guarantee that the series converges. There are, in fact, many series that do not converge that this is true for. For instance, if we have the sum of 1 over n as n starts at 1 and goes towards infinity, this is the harmonic series, this is divergent, even though this fact is true, that these terms do get smaller and smaller. They do approach 0 as n approaches infinity, but this will still diverge. So if you start with this fact, sometimes it diverges and sometimes it converges. However, if you look at it the other way, if we know that the series converges, then it is absolutely true that the terms have to get smaller and smaller and approach 0 as n goes to infinity. And with this fact, like I mentioned, if we can just show that these terms do not approach 0, then it's guaranteed that the series diverges. So we can phrase that as the limit as n goes to infinity of these terms. If this is not 0, then that sum of a sub n, starting at whatever you want and going to infinity, this would be divergent. So let's just try to prove that these terms do not approach 0, and if they don't approach 0, then we know for sure that it's divergent. So let me just make a bit of room for this, and we can rewrite our a sub n here, these terms. So we have that a sub n is, in the numerator, 6 plus 8n plus 9n squared, and then all of this is divided by our 3 plus 2n plus n squared. So we have this rational expression, and we need to show that in the limit as n goes to infinity that this does not approach 0. And to do that, algebraically, we can look at the highest power terms in each and divide the numerator and denominator by that highest power term. Or in other words, we can take our numerator and multiply it by 1 over n squared, and we can take our denominator and do the same thing, multiply it by 1 over n squared, so that we would get in our numerator 6 over n squared plus 8 over n plus 9, and in the denominator we get 3 over n squared plus 2 over n plus 1. And at this point, we can now take our limit. We can look at the limit as n goes to infinity of this rational expression here, and I'll just write it as a sub n. And what we can notice is that these terms where we have n, or some power of n, in our denominator, all of these are going to approach 0. Since as n gets bigger and bigger, the denominator gets bigger and bigger, but the numerator is fixed. So this overall fraction will get smaller and smaller and will approach 0. And that will be true for all of these. So that we get 0 plus 9 in our numerator, and we get 0 plus 1 in our denominator. So the limit as n goes to infinity of these terms here, this approaches 9. And since this does not approach 0, since these terms are not getting smaller and smaller, that guarantees that this series as a whole must diverge. It cannot approach some number since you're constantly adding a number to this that is bigger than 0. It's constantly changing rather than converging on some specific value.